Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, welcome everyone. Thanks for coming. Today, Arigo and I have the distinct pleasure of hosting Ivana Tosic from Rico Innovations in Menlo Park, California. Ivana got her PhD, I think, around 2009 from EPFL. Spent a few years after that at Berkeley at the Redwood Center for Theoretical Neuroscience, and then after leaving there, went to Rico. So we're very excited to hear what she's got to tell us. Thanks.
Thank you, Phil. Thank you for the introduction and for the invitation to come here. It's a great pleasure. First time for me at Microsoft Research here. So I am currently with Rico Innovations, but all that I'm going to talk about today I've done during my postdoc at the Redwood Center. So I'm going to talk about dictionary learning for 3D scene representation, and I will explain during the talk what dictionary learning is. So basically the whole idea and the whole goal of my of this particular work and of my research is what are the best representations for 3D scenes and how to acquire them, and how from the images and information that we acquired, how we build those representations. So this is joint work with Bruno Olshausen. He was my postdoc advisor at UC Berkeley, and Jack Culpepper, who was a PhD student at UC Berkeley, and now he is with IQ Engines, also in Berkeley. And Sarah Drewes, who was a postdoc at Berkeley in the math department, and now she is with Deutsche Telekom in Germany. Before going into 3D representations, I want to give you a little bit of motivation and go back to the fact to see how we actually captured information about 3D scenes. So there are many ways to capture, and here I show two most used ways to capture. One is if we have a network of cameras that is capturing a 3D scene, and we can have multiple views of that scene from different angles. Another way is to use hybrid image and depth sensors. So this is a time-of-flight camera from PMD, German company. And it captures depth information, and I will usually show depth images, depth map in color, where red represents closer, and further is blue, and gets also here intensity map or reflectance map of the object, or Microsoft Kinect, where you can have the depth map and you have the color image that are co-registered. So in both ways of capturing, we have rich 3D visual information, and it has many applications in 3D television, in surveillance, robotics, exploration, and just to name a few. But what is worth of pointing out is that depth or disparity is central to both these approaches of capturing 3D scenes. So here the depth is contained implicitly in just by the parallax between different views, and here we have explicit measurements of depth, like distance from the sensor. And we need that depth information if we want to interpolate in between the distant views. So of course we cannot have view of the currently with the current technologies, we cannot have views from every single point in space. So we can just sample that space of camera positions and then interpolate in between and extrapolate. But there are problems with depth, and main problem is its measurements are unreliable. So we get usually very noisy data. And here I'm showing you an example of from a time-of-flight camera. This is the intensity, the reflectance image, and this is the depth image. And if you kind of zoom in, you can see that there are a lot of kind of salt and pepper type of noise. This is much different than the noise type of noise we see in regular images. Or we can have from laser range scanners. This is a tree in front of a pillar, and you can see that there is errors in acquisition around the boundaries of the objects. And this is from structured light sensors, where you have missing pixels, where you have occlusions between two views in a scene. So the bottom line is that for different type of depth sensors, we need algorithms to do denoising, remove the noise, or inpainting to inpaint where there is missing information. And of course, these are both ill-posed inverse problems, and to solve them, we need some prior information about the data that we are reconstructing, so for depth. And for this, to solve it, we actually need good representations. And the idea of using representations to solve inverse problems is not new. It's been used for decades in image processing. And Fourier bases have been used for representing images, wavelets, and in the last decade we have seen a lot of people using over-complete dictionaries, where you have a much larger number of elements in your basis than you have, then is the dimensionality of your signal. And here I have just shown an example of a dictionary that's been learned from a database of images. So these elements of the dictionary that we usually call atoms, if you vectorize them and put them in a large matrix, you have a big fat matrix. And to reconstruct the signal, here I'm just showing an image patch from Lena, you need to multiply it with a tall vector. And if you want to do this really efficiently, you can say, well, I want this vector to be sparse, to have some small number of non-zero components. And if we want, now let's go back to our problem of noisy images. So what we will observe is not exactly this vector of the signal, but something with the added noise. So then the denoising problem, if we are using representations, becomes estimating this vector A, a vector of coefficients, to reconstruct our original signal. And in denoising, people for images usually assume either stationary Gaussian noise or Poisson distribution of the noise. But it's usually, for the Gaussian, it's usually considered to be the same distribution of the same variance of the Gaussian throughout the whole image. And for Poisson, it's also linked to the intensity of the image. So pretty well-known models for images. But what about depth? So in depth, we have seen that the noise is usually spatially varying. So that's what I will call non-stationary, but it's not in time. It's non-stationary throughout the whole image. And we can also add the time dimension, but for this talk, I'm just going to keep on still images, still depth maps. But also a bigger difference is that the statistics of depth maps differ from the statistics of images. So just by looking at depth maps, we can see, well, there is much less texture than we have in images, and we have much more sharp and oriented edges. So let's see if we want to represent with, to do denoising with wavelet thresholding, like the simplest representation, we get a lot of ringing artifacts around the edges. Well, we can say, fine, that's great. We know that because orthogonal wavelets are not really optimal. We can use curvelets that better represent boundaries, so we already get some better results. Or we can just say, well, we're not going to use representations. We're just going to use some local filtering or non-local. And this is with non-local means denoising. And
so that is done on that form.
This is, yes, this is all done on only on depth. So you can see, well, this is a great result, but if you want to zoom in into a bit of details, you can see that I have lost some details here. This is a part of my hair, and smoothed out a lot of the information in the depth maps. So we have looked at this problem and said, well, let's see if we can learn sparse representations of that. So not just start from representations that exist for images, like wavelets or curvelets, but let's learn them from the data. So in the rest of the talk, I will first go briefly through sparse representations, just the background. And please interrupt me at any time if you want clarifications on anything I suppose that people have already heard. Has anyone heard about sparse representations? Is there someone who is not familiar? Good. And we can go quickly through that. And then the two parts of the talk will be learning sparse representations for depth only. And then the second is a newer work. It's learning representations jointly on images and depth, so on intensity and depth. And for both of these, I will show you how we model the data, how we learn the dictionaries, and what do we get results on inverse problems. Okay. So sparse representation are also linear representations, like the transform coding of wavelets and curvelets. But the difference is now that we have this big dictionary, which is overcomplete, has a much larger number of elements of basis functions or atoms than the dimension of the signal. So our coefficient is a long vector, and to reconstruct it then becomes a combinatorial problem. So it's not easy to find these coefficients, and we have an infinite solution set. So what people have proposed is to look for a sparse solution, and there have been some suboptimal algorithms like the matching pursuit or the basis pursuit denoising. And I will just quickly explain the basis pursuit denoising in the next slide, because that's the type of algorithms that we use. And then another bigger problem is, well, great, we can get the coefficients, but how do we find this big dictionary? Like, nobody's going to give that to us. So for that, people have developed dictionary learning, or they're called also sparse coding methods, just from given data to learn what is the best dictionary for that data. Okay. So this is just one slide to go over how we find the sparse solutions once we are given a dictionary, and then we'll go into the dictionary learning problem. So if we want to pose our we want to find the sparsest solution to our reconstruction problem, basically we want to minimize the L0 pseudonorm of our coefficient vector, so to have the smallest number of non-zero entries. And this is NP hard. This is under a quadratic constraint that the approximation is bounded by some error. So what people then propose is that let's relax an L1 norm to an L0 norm to an L1 norm, and have that as our objective function, and keep our quadratic constraint, which is convex, and it can also be formulated as unconstrained. And the advantage, of course, that this is convex and easy to optimize. So that is the basis pursuit denoising introduced by Chen, Donovan, Saunders in 1999. So great. So once we have the dictionary, we know how to find a vector of coefficients. It's not necessarily the same solution as the L0 norm, but it's most of the cases it's a pretty good approximation. Then, of course, you wonder why would we use sparsity? And it turns out that this is a really good prior in solving inverse problems, such as denoising and inpainting, because it gives a good generative model of the images. And I'm just showing here an example again on the Lena and on the images, but I will show you depth maps in just a second. This is denoised using sparse representation in translation invariant wavelet frames. So just by adding over-completeness to our representation, we can get better results than, for example, just using plain wavelet thresholding. So just a simple example showing that over-completeness already gives us something, and sparsity as well. But what we can also do, and it's really important, that we can adapt this dictionary to signal statistics. So we don't have to use this translation invariant wavelet frames. We can learn our own. And this is...
So you're saying that you're learning the noise, the statistics of the noise, while you're learning the dictionary.
So at this point, I'm just saying, telling you the background, which is learning the signal, the statistics of the signal. Let's say you have no noise in your signal, or the noise is actually subsumed in the approximation error. So you said, I'm going to find a signal model up to this approximation error that well represents my signal. But for depth, I will show you just a sec. So this is... So people have previously proposed dictionary learning or sparse coding, and it was first proposed by Olshausen and Phil in 1997. This is the maximum likelihood learning, where they said, well, we'll have a linear image model, and for the learning, we're going to maximize the log likelihood that natural images arise from the model above, given that dictionary. So they posed it as this optimization problem to maximize the log likelihood over the set of dictionaries. And they have used images for training from this Van Hateren image database of natural images. And, oops, it's supposed to be. And then, okay, I have a dictionary after coming. But before I show you what they obtained as a dictionary, I'll show you how they solved actually this problem, because now they had a model of the signal to put into the model. So they uncoupled the conditional probability of the images given the dictionary and the coefficients times the prior on the coefficients. So this is important to put the prior on the coefficients because that's where we put the sparsity assumption on the coefficients. So if you put this prior to be a kurtotic distribution, which is tightly picked at 0 and heavy-tailed, and this one is just a Gaussian distribution if the noise is assumed to be Gaussian, it turns out that this objective function, that this optimization problem can be cast as equivalently as minimizing the energy, where energy has this form. We have the quadratic approximation error plus the L1 norm, lambda times the L1 norm of the coefficients. So you can see that this is exactly the same objective that is for basis pursuit denoising, except here we have unknowns which are both the dictionary and the coefficients. So to solve it, they proposed a two-step alternating optimization. So they have a big set of natural image patches, and they initialize the dictionary randomly. And in the first step, they fixed that dictionary and minimized the objective over the sparse coefficients. So basis pursuit denoising again. Then they fixed, in the next step, in the learning step, they fixed the sparse coefficients and minimize the energy over the dictionary. So that's the learning step. Basically, it's just you can do simple gradient descents. So you take gradient steps in the coefficients and then in the dictionary, and the coefficients in the dictionary until you converge. So, and starting from a completely random dictionary, they learned a dictionary that has oriented bandpass filters that are Gabor-like. So they look a lot like Gabor wavelets, and this was just learned from the statistics of the data. this was an important result actually in computational neuroscience, because they showed that this sparse coding can be also a principle for encoding information in the brain, because this emerged dictionary looked a lot like the receptive fields of neurons in the primary visual cortex in V1. Not just, the fact that they are bandpass and Gabor-like, but also distribution in orientation and in frequency. Okay, so that's it for the background. So do you have any questions so far? Because from now on, I'm just going to build upon this. Okay. Then we looked into how to learn these dictionaries for depth. And we had a challenge, so how can we learn it such that we are robust to this spatially varying noise? So we have to learn from noisy data, and the noise is not anymore stationary Gaussian noise that was assumed previously in the dictionary learning. So what we propose to do is to add another, so we had the linear model, dictionary times the coefficients, and we have the approximation error, and then we can put that to be stationary. But we have another type of error here, which is just due to the acquisition device, and we modeled it as a multivariate Gaussian. So we wanted to be general here and say, well, let's assume that each pixel has a Gaussian noise, but the variance of that noise can vary along the image. So some pixels can be more noisy, some pixels can be less noisy. And we are going to infer those statistics with also inferring the sparse coefficients. So we assumed a multivariate Gaussian noise, and this is its covariance matrix, and we assumed that these are the noise is not correlated between the pixels. So that's one of the limitations of the model. So how does that change our graphical model for the images? So we still have the sparse coefficients, we have the dictionary, and then we have different noise variables added to each pixel in the depth map. So this is just to highlight the differences with respect to the basic dictionary learning sparse coding method. So these are the new variables, the new noise that we have added just to be able to deal with different noise in depth maps. Okay. How does that change our learning objective, where we can still use the maximum likelihood? And now when we break down our likelihood, we have three terms. This term is the Gaussian distribution of our approximation noise, so this is fine. And then we have the prior on our coefficients. We can put that as a Laplacian, and a prior on our covariance matrix, so a prior on our noise. So then for the prior on the noise, we decided to do a non-informative Jeffreys prior, just to not put any structure on the noise, to stay as general as we can. And so now what is the difference is with respect to the regular objective in dictionary learning, is that we have another set of variables that we need to infer, and then we have one other distribution and one other parameters here. Okay. And then the energy function is also slightly modified. So here we have the sparsity term, but which remains the same. But in this term, we have the log of the variance, which is due to our Jeffreys prior, and then the error at each pixel is divided by the 2 times the variance of the noise at that pixel. So these are also unknowns that we have to find. So it's pretty simple formulation, and it can be also modified if you know some specifics of your noise variance, how it's related to the signal, you can put here as well. Mm-hmm.
So it seems there are a couple of common models that I've seen for error variance in depth images. One is that it varies square of to depth. The other is that it it varied. It more along the lines of a Poisson. Noise model. The variance is the brightness.
Yes.
So, but this doesn't seem to be motivated
No.
really by either of those.
No. So we wanted to keep it more general as we can. So we can adapt it to take that more specific relations into account, but we just wanted to keep it as broad as possible, so it's not always related just to depth, that you can use it in other scenarios too. But if you if you have that kind of deterministic relation, you can easily put it, and it's going to simplify, finding your variance. If it's related, then you don't have to infer it anymore. You can just relate it to the signal.
So if it's, say, proportional to f, I guess. F is the depth.
You can still use, yes, you can still use the same objective. It's just that this might then become harder to optimize.
Well, in the case of time of flight, signals, it would be the brightness.
Yes.
And you would actually have to do that.
And you can also change the prior. This turned out, we wanted also to infer this so that we know the reliability, how reliable is each depth estimate. So basically we wanted to see for each measurement of the depth, how reliable it is and how well it fits to the signal model. So it not necessarily always linked to the acquisition device, but occlusions or some other noise.
So the lambda multiplier there is some sort of Lagrange multiplier.
Yes.
Can it be spatially varying as well? Let's say I have my depth map and I know exactly where the bad measurements are. So can that be taken into account while actually basically making the lambda spatially varying as well? Does it make the solving the convex problem harder?
So what you can do is use these solvers that actually find your lambda while it's finding your solution for each patch. So it finds the best lambda for each patch. So it's already, you can already use a solver that deals with that problem. Or if you know how to estimate lambda yourself, then you can put it there.
But even if it's spatially varying, it doesn't affect.
You would. Well, you cannot vary it here for each pixel. You vary it for each patch in the image.
Per prior, basically, per little.
Yes,
atom.
yes. It might be possible to do it per pixel. I think there is some work on that, but I can't really remember right now. But yes, you can. You can vary it per coefficient. Yes, the work that I've seen, I can point you to the reference, is you can change different lambda for different coefficients. They call it kind of like the scale model. But that's kind of different that you were saying.
So it seems like your model assumes that the noise is only dependent on the pixel position instead of dependent on the scene. So for the same pixel, if the scene changes, the noise characteristics will change.
So right now I'm just doing static depth maps. It's not a video depth map.
You mean like the scene does not change?
Well, it's just static, yeah. It's just like still depth maps. If you do it image per frame, you can just find different variance for each of the pixels in different frames, or you can constrain it to smoothly change from one frame to another. But it's different. The point is that it's different per pixel. So now how do we solve this, how do we learn the dictionary? So we have two parts again. We have inference first. So we need to find all the coefficients and we need to find the variance for each noise per pixel. And we solve that in an iterative manner. So we first initialize our sigmas to be equal and very large values. So we start from a hypothesis that all the pixels are unreliable. And then we infer the coefficients, then we fix the coefficients and solve for the variance, and this has a closed form solution. So usually it takes just a couple of iterations between these two to find the solution for the A's and the sigmas. And then once we have that, we solve for the dictionary. And this is just to show that it's averaged over all the all the examples in our image-based data set. So it's the similar principle. We have inference and learning. We iterate. It's just here in the inference step, we also find the variance of noise per pixel. Okay.
Sigma I squared, that equation equals to 0 if the top is, if fi minus fi hat is less than the threshold?
Yes.
Would that cause your previous equation to go to infinity?
No, because we have this sigma 0 term which is added to it. It will if this, so the sigma.
Yeah, so sigma I is at the bottom, so if it's 0, then
yes, some good point. So basically this, into this sigma I, we add, I put it here to be more, just to simpler, this sigma I has the plus the sigma 0 squared, which is this approximation. So yeah, basically sigma I is the sum of the sigma i's plus this. Yeah.
Sigma 0
Sorry,
is
it's
constant.
yes, sigma 0 is constant. Good. Yeah, that's a good. Just for like ease of representation. Basically this sigma I hat is sigma I squared plus the sigma 0 squared. And that's how we limit it. So that's why it's here. We don't let it go negative, because if it goes into negative, then it becomes 0.
so when fi minus fi hat is big, then you are ignoring basically the difference in the f previous equation.
Sorry, can you repeat that?
When the difference between fi and fi hat is big, basically the denominator becomes
Large.
same as the top.
Yes. So it's
So you're
reduced.
just ignoring that term.
Exactly. So if the measurement doesn't really fit the model, and you just isolated it doesn't fit, then it reduces that term and says, well, this is not reliable measurement because it doesn't really fit well our model. Okay.
You assume you already have dictionary here, so you already. So here you only solve
Yes.
by the sigma. I thought the dictionary itself also is a variable. It's also
That's the next.
Yes. Yes. So
That's excellent. Okay.
that's the learning.
Okay.
Yes. So here we fix dictionary. We start from a random, and then here we learn it. We optimize over the dictionary.
So there's a lot of variables here. Like your input is just f. It's a noise f. So basically you're doing decomposition. You're doing the sort of decomposition. We're given f.
Yes.
You want to solve for a and this coefficients, dictionary, and also the noise model. It seems like it's really undetermined problem here.
Yes. It's hard.
Maybe reliance on the prior as opposed to
Exactly.
Yeah.
Exactly.
Just, are the iterations always converging? Is it because of the convexity? Or-
So each step, so because the objective is convex, each step is convex, but it's not necessarily the whole objective because it has multiple.
So generally, it works.
I have never gotten a non-convergent dictionary unless you don't, unless you have really small number of training sets. Yes.
Are you learning one dictionary per image?
No, one dictionary for a database of images.
Okay. Because I thought you were learning this from one image.
Oh no.
Because you assume that who I'll ask you what is before is the noise model per pixel. That it's only a pixel what can sin. Right?
Oh, that's what you meant by scene. Yeah. No, it changes for image to image.
So if the image is different, that means the scene is different. So then when scene is different, the noise model will be different, like even on the same pixel. So that means you will have to use different sigma for different scenes.
Yes, that's why we infer sigma for each pixel, for each scene.
Per image?
Yes, per pixel, per pixel per image. Yes.
Per image.
Per pixel per image.
I see. Okay.
So yeah. And here you see we average for the diction. So this is done per each patch, and then because it's independent, you can just do sparse coding for each patch. But then here, for learning step, we average overall the patches, overall images.
The positioning of the patches is just regular.
It's
regular
random.
grid.
Yeah. Randomly chosen from the. Yes. They take a lot of images and then you randomly chose patch. So I can show you. This is from the Middlebury benchmark. We took all the depth maps, and I think we had something like 30 depth maps, and we extracted 16 by 16 patches of 16 by 16 pixels. These are some examples. And so here, most of the irregularities are the occlusions or disocclusions. So these are either missing pixels, and we don't mark them as missing pixels. We just let our algorithm see if it can figure out that these are non-reliable data. So we have learned the dictionary, and I will show you here in grayscale because I think it's easier to see. And what we saw is that we have a lot of oriented edges. They are a bit different than for the images. They are kind of more sharper edges. And we got some couple of slants like here. We think that this kind of used for the ground, because usually in this depth maps, the ground is kind of tilted. It looks because the sensor is looking that way. And this can be multiplied by positive or negative coefficients, so it doesn't really matter if it's white in the front or black in the back. But the biggest conclusion is that it is different than the dictionaries people use for images. So we have tried to see, well, how better do these dictionaries do? And we have done that on a denoising task. So this is just a mathematical formulation of a denoising task. So in denoising, we now have our learned dictionary, and we have our coefficient, and we have our noisy image. Sorry, here. So we want to reconstruct like a denoised image f hat. So what we need to do is to infer both the coefficients and the covariance matrix of the noise for that patch. So here dictionary is fixed, so it's just our inference step is the same. And so I'll show you here example. First, these are first real depth maps, but synthetic noise, just to be able to see, to have the ground truth and to compare against it. So this is an original depth map. This is obtained with a laser range scanner. This is from Young and Purv's database, so Purv's database. And we have added non-stationary Gaussian noise. We have corrupted 1% of the pixels in depth maps. And the variance was randomly chosen for each of the pixels. And we have done total variation denoising and got, resolved that smoothed out some parts, but still left some of the noise undenoised. The curvelet thresholding gave also some really bad results. Non-local means gave nice smoothed results, but it lost a lot of the details. This is a trees forest in the back. And this is the result we obtained with our non-stationary sparse coding. And
just a question. So when you compare different algorithms like these, of course, each algorithm might have thresholds or parameters. So do you try to be fair and to adjust them?
Yes, I tuned the, like for total variation, the regularizer, the lambda. I chose the best one for non-local means and for curvet, yes.
So I'm trying to understand what exactly going on here, and I feel that exactly, I mean, you're basically trying to learn the dictionary under the condition that there's a lot of outlier pixels. So in the literature of parameter estimation, there's a lot of work on robust estimation of parameters, where you can do all kind of things to kind of make the estimation robust. And from the way you threshold, it seems that what you're doing is basically just take away the outliers in your process and just learn from the remaining pixels.
Well, you also estimate something about those outliers. You're not just thresholding them and saying these are useless. You're also, well, I have a reliability measure.
I was doing that because when it's greater than sigma 0, you basically throw it away because your second term.
No, when it's smaller. When it's smaller than sigma 0.
Minus fi hat square and minus sigma 0. So you add sigma 0, then make it fi minus fi hat, and the top was also fi minus fi hat. So basically that data is being thrown away immediately.
If it's below sigma 0.
Yes, and if
it's subsumed in the approximation error, we don't care about it.
Below sigma 0, then you are using the data, but if it's above sigma 0, then you just throw it there.
No, it's just appropriately weighted.
No, you're weighting.
It's thresholded when it's.
Previous slide.
It's
yes,
threshold.
Here, right? So
yeah.
if it's on the top condition, then it's 0, which is sigma 0. So you're weighting every pixel with the same weight, sigma 0.
Plus additional 1.
And the second term, when you put it there, because the bottom is sigma I squared plus sigma 0, so you end up with this 1/2 fi minus fi hat square. So, but the top is also fi minus fi hat square, so you end up with a 1, a constant. So you're throwing away that pixel.
Oh, I see what you mean. No, because when you are, because in the first step here, you are inferring A, and these sigmas are from the previous iteration. So you're never dividing with the same. This is, you solve it after, and then you go back.
Well, in robust estimation, you can say I threshold, I get rid of 10% of outlier, I estimate a parameter, I re-infer the outliers, and then I threshold again. This seems to me very similar, right?
Well, I will show you an example. So we get per pixel some estimates of the variance, and I will show you how they look like. So they are not thresholding. There is some variability in them. So this is just similar, showing the results averaged over different images in the same pervs database. And this is the non-stationary sparse coding result that performs much better than the other ones. And this is just, we corrupt it with a different number of bad pixels. And so I think maybe here you can see what we get from the data. So this is from laser range data, the one that I showed before. And this is the original. When we put into the non-stationary sparse coding, we get an estimate. And then we get the reconstruction. And then we also get per pixel the inferred variance. So you can see that it has different values for different pixel. And then you can use also this data if you want to do further processing of this, you can use this data to kind of put a reliability measure on each pixel. And this is what you get from non-local means. So you also remove some of the noise, but you smooth out some small details like here. And this noise, which is basically correlated noise, we were not able to denoise because it doesn't fall under the assumptions of the model that the noise is not correlated. So this is the limitation of this algorithm. But I think the best property is that it gives us both the denoise, the image, and denoise depth map and inferred variance.
It seems to be mostly on the edges.
Yeah, so we can get some of the correlated, so these are correlated along the edges, so they are not just single pixel outliers, but when it has a lot of correlation, then it has problems. And we have done that also on the time of flight data. So this is the original depth, and this is the denoise. Then I can just, oh, it doesn't zoom in. Sorry. Basically, we removed all these pixels, and then we kept some of the fine details of the depth map. And we can also do inpainting, just as an example from Kinect depth maps. Again, we can inpaint well around the edges, so here, but when we have big pieces of the missing information, which is bigger than our patch size, we cannot fill it in.
How big was the patch size?
16 by 16. You can learn it larger, but then you need bigger machines.
What's the dictionary size?
We learned it was just complete. You can also make it more over complete and it will be better. So it was 256 elements.
Can it somehow be done hierarchically, where you start with smaller patch sizes and then where you get it right, you skip them, and then for the bigger ones you just get the area where it's bad?
I think yes, and I think some people have done it in a kind of like a multi-resolutional dictionary learning. Yes, there's also work on that. Yeah, that's a good point. Okay, so I will go now through the second part, and it will be a bit quicker, but stop me please if you need some more information. So here we decided to go step further and see if we can learn multimodal representations of intensity plus depth. So it's pretty easy to see that there is a lot of correlation between the intensity reflectance this is in time-of-flight cameras and depth, or the intensity and disparity in structured light. So here we need two model representations. Basically, we need our dictionary atoms to have two parts, their intensity part and their depth part. And let me quickly tell you why some very simple models that you can think of will not work on these two simple examples. So this is just synthetic, just illustration. If you have like a 3D edge, it is observed with the hybrid sensor, you have an image, piecewise continuity, and depth again. Or another example, if you have a slanted surface with some texture on it, let's say a sine grating, if you look at it, the image will be a chirp, and then the depth will be just a gradient. And which you can say, well, let me just put on top. I will put intensity on top of the depth and put each atom to have its intensity and depth part. Just put one vector on top of another and multiply with the same coefficient. So in the example one, you can do that. But what will happen is that because you have the same coefficients for both intensity and depth, you will have to put the variability in terms of the contrast within the atoms, which would lead to a combinatorial explosion of the dictionary. So we cannot do the stacked model. What people then have proposed is let's say you have a common dictionary model. People refer to it as joint sparsity. well, you have the same dictionary and two different coefficients. And here that would be great. We just put like a hard wavelet or step function and multiply with different coefficients, and that will account for the contrast difference. However, in the second example, we won't be able to use this model because we cannot have one atom that can represent both a slant and a chirp. So the conclusion is that we need a model that has different atoms and different coefficients, but still model the correlation between two modalities.
Have you considered encoding the brightness in the magnitude of a complex number and the depth in the fields? Because then I mean, this is also done in MRI.
You can do that, but then you have a problem of phase warping, wrapping, right?
Yeah, you have to assume so.
Yes. It has been, I can point you to work, it's been done for videos, not for depth, but with like optical flow type. What we proposed is to have this like a sparse model for image, sparse model for depth, and then just have coupling variables that multiply with the magnitudes to give the coefficients. So these ideally binary, but we can relax to be between 0 and 1. And they just say, well, if it's 0, we are turning off both intensity and depth. If it's 1, we are turning them on. So at the end, we want to have sparsity on these coupling variables. And you can put that into a system model. So you have atoms for intensity, atoms for depth. These are the magnitudes of the coefficients per for intensity and depth, and these are the coupling variables. And then you can have different noise in the intensity and depth. So then becomes a problem, how do we then do inference? So if we look at it, put it as an optimization problem, we want to minimize the L1 norm of our coupling variables. So since they are positive, this is the sum. And then we have a set of constraints. This is the quadratic constraint representation of the intensity. And here I'm just doing for the stationary type of Gaussian noise. It's another step further to do it for the non-stationary. And the same for depth. And let's just say that our magnitudes are bounded by certain values. They can be big, whatever. So this problem is bilinear, so we cannot optimize it in a straightforward way, but just doing a simple change of variables where we put that A is m times x and B is similar, we can get a convex, and it's a second order cone program, and we can use already existing solvers to find the coefficients. So this optimization problem gives us the values for x and for the a's, for the A and B, and equivalently for the magnitude. So we named it joint basis pursuit because it jointly finds the intensity and depth.
This like xi is also semi-dependent.
So for each patch, for each pair of intensity and depth, we get different x variables. Yes. So x, a's, and m's are all hidden variables. They're estimated for each image, and only the dictionary, these are the parameters that are estimated for the whole database. So then, again, in a similar way, we can have a two-step iterative process to learn the dictionary. We initialize it randomly and then do the joint basis pursuit to find the sparse coefficient vectors and x as well. And then use that in the learning just to learn the dictionaries and iterate between these two steps. So very similar. And we have learned it again on the Middlebury benchmark database. We used both intensity and depth. And we have learned the twice over complete dictionary. And here I show in each of these little panels an atom that has its image intensity part and disparity part, or the depth part. And just by looking at it, we can see that there is coinciding edges, which we would expect because an edge in 3D would induce an edge both in intensity and depth. And there is a texture. We saw that there is sometimes we have a slant in depth and a texture in the image. So this type of atoms, which are a bit more rare than these ones, but they still exist. And we can also plot a scatter plot where on this axis I've evaluated the gradient angle of a depth atom. So basically this is the gradient angle, the normal. If you would see it as a slant, it would be like a normal on the surface. And it's texture part, which I just fitted to each atom a gabor and found its orientation. So if you do a scatter plot, and here each point corresponds to an atom in the dictionary, you can see that there is like a big diagonal structure. A lot of points are on the diagonal. Basically, there is a 90-degree angle between the gradient and the gabor orientation. And just for comparison, I didn't show it here, we did a similar experiment with the group lasso algorithm, and it gave us completely uniformly distributed. It didn't at all give us the same tendency of the correlation between these two. So this was an interesting result because a lot of people have looked into the statistics of intensity and depth, and they found out that closer objects tend to be have to have higher luminance and higher intensity values. But this was, to the best of my knowledge, the first time that we have shown that there exists some type of correlation between the gradient angle of the depth and the orientation of the texture. And of course, we have done some inpainting experiments just to show that if we have dictionaries that are learned both on intensity and depth, we can get slightly better inpainting results than just the depth dictionary. Here we removed 90% of the pixels from the depth map. And here I removed 96% just to see how far we can go. And just from 4% of the pixels plus the intensity, we can reconstruct this depth map, which is still blurry and it's not perfect, but it's really from 4% of the data, which is, yes?
So that's for missing pixels are removing both the depth value and the image value?
No, just the depth. Basically, we are relying on intensity to give us the, it would be a good experiment to try, removing intensity and keeping depth, and removing both at the same or removing both at different.
So basically, the correlation that you have learned during the dictionary can be used.
Yes. It's a prior. So if you see a gradient or oriented texture in the intensity, it will try to fit a slant, or if it finds an edge, then it will try to fit an edge in the depth.
I'm not understanding why that's blurry.
That's
Just from missing, I mean, if it weren't missing anything, would it be blurry?
So I think that's blurry because these models are essentially linear. So they're kind of, you're linearly combining these atoms. So if you're bad at estimating one, you're just removing some of the, it's not like a layered model in a scene per depth where you would nicely represent edges.
Is lambda turned up so high that it's not sparse? Or?
So here, because we have used this this solver, we don't even put the lambda in. So it finds the best lambda to solve it. For the group lasso, this is comparison with the group lasso. I just ran it for a bunch of lambdas and I took the best one. If you have if you turn up lambda, it will be smoother for the group lasso. But here, you don't have that option to tune it.
Also, is there averaging because you have many patches that must be combined, right? So maybe there's some averaging.
Yes. Oh, that's two. It's overlapping patches, but it's a linear model. Yeah.
So in here your priors are still 16 by 16?
These are 12 by 12. Yeah, we had to reduce them because now it becomes the dimensionality of the problem increases.
Is this the entire dictionary?
Yes.
And
Yes.
how many elements?
So 288.
What's the data set that you use for training this? I mean, how many images you need for training this? How many images do you need to train this?
This was like all the Middlebury that I could download. So I think it's around 30 intensity depth pairs, depth images. But within each image, you take random patches which are 12 by 12. So you have a lot of data. This is kind of the data set that I found that I can do this type of training on. I'm not aware of any other database that I can use. Maybe maybe from the MPEG data set. Yes.
I think it was your next slide here, you found a relationship between the angles of depth and intensity. Do you think that same relationship would hold if you just looked at raw patches from the depth and intensity rather than the dictionary?
That's a good question. I don't know. That's something worth checking. Yeah. I suppose people would have already looked at something like that, but yeah, I know that we tried it. I can show you. I have one slide. I think it's this one. So this is a plot with the group lasso, and it's completely different. If you do dictionary learning with group lasso, you don't get that. I can maybe also show you this. So I said that some people have already looked into the relation between luminance and how close the objects are. And I have looked at the same thing for my atoms. And it turns out that in atoms also we get that closer. If you look at the closer and further, then you also get the closer objects appear brighter. So it's pretty dominant. So here is the bright surface is closer, and histogram, and the red one is when the darker surface is closer. So we got the same tendency that people have already observed. Yes.
So just to be clear, if you didn't have even any depth pixels in a 12 by 12 region, you couldn't inpaint that, right? There's no propagation from neighboring cells or anything.
You would have to learn larger dictionaries. If you have a whole, if you don't have any data, you don't have a system.
So larger as in bigger patches, or larger as in a bigger number of patches?
Bigger patches. So if you don't have any data, your observations are empty set, so you don't have anything.
You get any blocking artifacts?
So what we do is usually average, we are shifting patches and then averaging. So if you don't do that, you can have the blocking artifacts. Yes. So I think on this ones I moved every 2 pixels and then averaged, not every single pixel. So yes, so just I like always to conclude with these representations of David Marr, just to show you where I think we are with the sparse representations right now. So he put these representations going in from the pixel representations to kind of edges and blobs in images, to 2.5D representations where you take into account the local surface of orientation and discontinuities, depths, etc. And these are all kind of viewer-centered representations. And these are mostly what we have worked on so far. So what I presented today is mostly in this block. And to go through 3D representations that are object-centered, it's still a part of future work for sparse representations. So I think that's it. Thank you. So please, if you have any further questions.
How would this work? Let's say I have prior knowledge of my like, for example, most of my patches are like locally planar, or I know exactly. Most of my stuff is going to happen inside rooms, and I have a lot of very planar surfaces. Would that would add in like an extra term to the minimization problem that basically enforces that somehow? Would that help, or is it not necessary if my training set just has only that?
So this is a completely non-parametric learning. So we are learning pixel per pixel for each image patch. So if we have 12 by 12 image patch, we have 144 parameters per patch. If you know that you have surfaces, then you say, well, I'm just going to learn a normal to that surface that will completely define my surface, and that will have 3 parameters, right? So you can reduce the number of parameters. I don't know how your objective function will look like. It will be convex or not, but you are definitely reducing the number of parameters.
These priors should be scale invariant, right? So like because it's equivalent to thinking if you get closer to your subject or further away,
so there are people who have, tried to do like a multi-scale, do like larger objects or smaller objects. I have not seen much difference in the way the dictionaries look like.
So there was the 12 by 12 could be scaled to any size with the same priors, right? So you could, like if you had a patch that had a 12 by 12 patch that had no depth data, you could apply your entire dictionary but scaled out so that you're basically reusing the same priors but on a larger scale. Right?
Well, you can. It just you're filtering basically the higher frequency from your data, right? If you're just upscaling, you won't be able to reconstruct higher frequency information from.
Sure, but you would still be able to inpaint things that had patches that were completely devoid of depth data. So if you had a big region with no depth data, you could inpaint that using the same dictionary.
Yeah, that's good.
It's basically tantamount to shrinking the original image, applying your algorithm, and then scaling it back again. So then you could inpaint larger regions.
Yes, that's a good thing to try. Good idea.
Thank you very much.
Thank you.